Hey everybody, it's Richard again from the University of Birmingham in the UK. Excited about this one because in this talk I'm going to talk about our general sample size framework for developing and updating a predictive algorithm with application to clinical prediction models. It's just been published in BMC Medical Research Methodology and extends and generalizes the sample size work that we've done in the past. So it's a really important one for me personally and for our team, and I'm really happy to share it with you in this talk. Okay, let's have an introduction before we get to the main stuff. Right, so what is the clinical prediction model? So quickly, because I assume most of you watching this video will know, but a prediction model is an equation, for example, based on a regression, or an object, a black box, for example, based on a machine learning method, which is used to estimate or predict in an individual their outcome, conditional on values of multiple predictors sometimes called features, characteristics. Basically, based on the values of the predictors for an individual, we can make conditional predictions of outcome risk, outcome value, and this is then used to make clinical decisions and to help counsel patients. For example, when you're about 40 in the UK, you'll have your Q-risk score, and that will tell you your 10-year risk of cardiovascular disease. If that's deemed to be high, then obviously you need to make lifestyle changes. They may even consider putting you on a statin. The Nottingham Prognostic Index is another one that's very well known for breast cancer survival probability. Such models are producing predictions, and therefore their performance needs to be assessed in terms of their predictive accuracy. This can be examined by things like the C-statistic, the area under the curve, the calibration curve or calibration slope, clinical utility such as net benefit, and so forth. There are thousands of prediction models developed each year in the medical literature. Very few are actually used, and that's because methodology standards are generally poor in the way that the models are produced and evaluated. A major issue is sample size. So sample size for model development is often very, very small. We've done various reviews. For example, machine learning methods, 82% didn't justify their sample size. In a review of COVID-19 models, 67% trained or tested using an insufficient sample size. Why is this important? Well, we showed in a paper in Lancet Digital Health that small training datasets lead to models that have reduced predicted performance. This is something that I call model degradation. So it means a worsening or a lowering of performance compared to what you could have obtained if you had a bigger data set. When you have small data sets and small sample sizes, small numbers of events, it leads to models that are not likely to give reliable predictions in new data. So that means they're likely to be miscalibrated, they're likely to have lower discrimination performance, lower C-statistics, and crucially lower clinical utility. That means lower benefit in terms of the model being used to inform something to guide decision making in those individuals, such as when to start treatment, when to monitor patients more closely, and so forth. It also could mean that we lead to unfair predictions. So this means that if we have smaller data sets, then there are going to be some groups within that data set that are not going to be well represented. So for example, we may have a data set that's mainly of whites, but then the data set has much fewer non-whites and fewer non-whites that have events, and therefore the predictions for those that are not white are very uncertain, much more unreliable, and that's perpetuated when you have small data sets. So if you want more about that, then I've given separate talks on the relevance of sample size for AI research, so check those out. So in terms of medical research, we usually, in most medical research environments, have a sample size calculation. So before we do our study, before we collect data, we work out the sample size required to do that research. So in prediction modeling, there are existing sample size guidance. Used to be based on things like 10 events per variable, but scientifically we've moved a long way from that now, thankfully. In 2020, we proposed how to calculate the minimum sample size to develop a prediction model. And this was based on regression theory. The aim was to fundamentally estimate the average risk precisely. So make sure that you can at least estimate the average risk in a population precisely. and make sure that the sample size and the number of predictors minimises the amount of overfitting, because more overfitting leads to less reliable predictions and leads to this concept of model degradation that I spoke about before. So we could think of a measure of overfitting is the amount of shrinkage needed for predictor effects, and if we targeted a shrinkage of 0.9 or above, so the shrinkage is 10% or less of the original coefficients, then that is in some sense small. So that's what the original calculations aim to do. This has been extended to think about stability of individual risk predictions, not just the average risk, in various papers. And the work is embedded in a package called pmsampsize in R, Stata and Python. Here the user specifies the number of predictors they're thinking about including, more specifically the number of predictor parameters, the anticipated C statistic or R squared of the model. This could be based on, and usually is based on, previous models in the field. And the calculations are really, really quick because they use a closed form solutions based on regression theory. So it takes half a second to produce the solutions for the sample size needed, given your anticipated sort of maximum C statistic that you think you can get, and the number of predictor parameters you're thinking of putting in. And pmsampsize has been really well used. I think we've had 100,000 or so downloads of that software, and it's had a really big positive impact, and hopefully has encouraged people to think more crucially about the sample size that they need to develop a model. But it's not perfect, and this was a really nice paper shown by Pavlo et al. In 2024 that pmsampsize, and more specifically the calculations behind pmsampsize, sometimes give the minimum sample size being too small. For example, that the closed form solutions that give you a target sample size to ensure that the shrinkage factor S is 0.9, sometimes that closed form solution is not a good approximation. So they propose a simulation-based approach where they, based on a particular sample size, they repeatedly develop models to see what the average shrinkage is, and then they work out the sample size to target the 10% shrinkage factor, essentially. Really lovely paper. Like I said, we've also extended the work to individual level stability, and that's in a package called PM Stability SS. There, the aim is to target precise confidence intervals around individual risk estimates. And again, this is based on regression theory. All of this stuff that I've just mentioned is applicable for binary, time to event, and continuous outcomes. And Rebecca Whittle in particular has extended some of the work to continuous outcomes. So there's been a lot of productive work in this area, but as I've kept saying, this is tended to focus on theory based on regression. So the concept has been a lot of the time that, okay, well, what do we do for other methods, such as, even like penalized regression methods like the lasso, and going beyond that to things like random forests or neural networks or something like that. The premise has always been for me that those methods tend to be more data hungry and need more data than the minimum for regression, because they tend to allow by default nonlinearity and interactions, some more complexity. So I always thought that pmsampsize still gives a minimum required, but it's it could be that you need a lot more, and so we needed something else to address that. So bringing this all together was important. We have various different approaches, like I said, the simulation-based sort of idea, the closed form pmsampsize approach, the PM stability sample size approach, and we needed to go beyond regression as well. So how do we do this? So this paper that's just been published in BMC Medical Research Methodology aims to address that. A general sample size framework for developing or updating a predictive algorithm with application to clinical prediction models. So this is the premise of the talk today, is to sell that paper and to explain what we've done. So in particular, I'm going to talk about the framework that sample size paper recommends. This is a general Bayesian approach to sample size derivation. The general idea is that we anticipate the posterior or the sampling distribution of predictions at the individual level based on the model development approach that we take, which could be regression or anything that we wanted. And we draw those samples from it, and we look to see from those samples the amount of reduction in model performance compared to some true reference model So this is going back to the idea of degradation again. In this talk, I'm going to show that this concept embeds all previous sample size calculations that I've mentioned. More importantly, it allows any performance metric to be considered, whereas the ones before I've just focused on calibration, slope, and overall risk precision, and is flexible enough to allow any model development approach to be taken, regression, machine learning, whatever it is. Let's just start with some key terminology. So I'm going to use the term reference model a lot. By reference model, I am referring to an assumed true model for a set of predictors. So the user is going to specify, to do the calculation, the user is going to specify the true model, the reference model, and this means specifying predictor weights, so the weight or the predictor effect, if you like, the C-statistic of the overall model, and the average risk in the population. We'll talk about how you do this, but in general, there are hundreds of models out there already. So usually there's a model in your own field that you can look at and say, okay, the C-statistics of existing models are around such and such, maybe 0.8, maybe 0.7, and there are these variables that are always included, so we could look at those and we can think about what their weights would be. And we might know the average risk in the population, and we can put all these things together. It's like bringing in prior information, like you would do in a Bayesian type approach, to inform your sample size calculation. And let's not forget, this is done in all areas of medical research. So, for example, in a randomized trial, when you're doing a sample size calculation, you have to say, well, what do I think the treatment effect is going to be? What do I think the prevalence of the outcome is in the control group, and so forth. And the other key term, like I've mentioned a lot already, is model degradation. But just to formally define this, this is the developed model's performance minus the reference model performance. So that the concept is you cannot do as well, unless your data is infinite, you can't do as well as the reference model performance. So the reference model performance is the best that you're going to do. And the developed model's performance will be lower than that. So the C-statistics will be lower, the calibration slope will be away from 1. The net benefit, the clinical utility of the model will be lower than the maximum net benefit. The reason for that is due to sampling error. So because you've got noise, you've got uncertainty in your data, you're not going to estimate the predictor outcome associations as reliably, and therefore there's going to be worsening of performance. This is related to the loss function. It's sampling error is also known as epistemic uncertainty or the model-based error. People from a decision theory perspective may think of this as value of perfect information. So if you had perfect information, how much would you gain? So all these concepts are embedded in this more general, broader notion of model degradation. Right, let's move on to the methods. So the reference model. So let's come back to that again. Any sample size calculation assumes a truth. And so the reference model is a prediction model equation that we specify as our truth. Like I said, we can't do better than the reference model. So our key question is, for a given sample size n, what is the anticipated degradation? This idea of a reference model aligns very much with Sir David Cox's response to Bryman, where he argues the merit of a formal model to guidance examinations of uncertainty. So just to take a step back from that, what I mean is that even if you think you're going to be developing a model using a random forest or a neural network or XGBoost or something like that, where you're not going to be able to write down the equation, it's important to think about a reference model in terms of a regression. Because with a regression equation, you can transparently specify the predictor weights, make sure that the equation relates to a particular C-statistic and a particular average risk in the population of interest. So by specifying that in a transparent way, you can then look to see what's the degradation compared to that. And that degradation can be for a model that's developed using machine learning compared to the regression equation. And the regression equation could include complex terms, interactions, nonlinear terms, as you feel is appropriate. But it's important, I think, to be very transparent, particularly in healthcare, to say, okay, we're designing a study specifically to ensure there's clinical benefit. Let's have a look at the clinical benefit we anticipate compared to this hypothetical reference model that, if we had perfect information, we'd be able to obtain. And this is sort of what David Cox is referring to here when Bryman is talking about the value of machine learning. And David Cox says, well, formal models are useful and often almost, if not quite, essential for incisive thinking. They indicate the uncertainty that would apply under somewhat idealized, maybe very idealized conditions, and as such are often lower bounds to real uncertainty. So by framing this in terms of the reference model being a regression, you can transparently understand the uncertainty relative to that. And it gives you, like you said, some lower bound to real uncertainty, even if you're developing models using a different approach. Okay. So our general sample size framework is based on the reference model and the chosen sample size. What we're going to be doing is we're going to be trying to anticipate sampling or posterior distributions of model predictions, which are then going to lead to anticipated sampling distributions of model performance and degradation. And this is all conditional on the target population of which you want to be doing the model training in and the model deployment in, the predictors and the candidate predictors that you're thinking of putting in your model, like I said, the chosen reference model, and the modeling approach. So all those things are important because the sample size that is required is conditional on these things. How are we going to implement this framework? Well, we have two options. One is to take this fully simulation-based approach. This will be exact. It will allow any modeling approach, but computational issues may abound because obviously simulation requires repeatedly sampling, repeatedly fitting models and so forth, and so therefore it could be slow, particularly for some complex models like some Bayesian penalized regression models. Or we could use some approximations. And remember, I taught you already that pmsampsize uses an approximation already based on a closed form solution for one particular metric, which is the calibration slope or the shrinkage factor. Here, another one that we talk about in the paper is using Fisher's information matrix. So this is approximate. It's based on larger sample theory. We also talk about how you can combine that with some priors in a Bayesian context. So that really does speed up the Bayesian sample size calculations compared to the simulation-based approach, but it's approximate. So because the approximate method is approximate, I want to focus mainly today on the simulation-based approach. So let's go through the steps that you would need to invoke to do this calculation. The first one is the setup phase. Here, you choose a sample size that you're interested in evaluating and a set of candidate predictors. Now, the sample size could be, for example, based on the minimum that pmsampsize recommends. It could also just be the fact that you've got a dataset or potentially got access to a dataset in which you know the sample size of it, and therefore it's fixed. So you're going to say, okay, well, I've got a dataset, it's got 1,200 people in it. I'm going to do the calculation based on those 1,200 people. And the set of candidate predictors, well, again, we need to think about that. And the calculation may be able to help us tell us how many parameters we can safely look at without degrading performance too much. But like I said earlier, this could be based on previous models, obviously variables that are in your data and so forth. We're going to specify our reference model. Like I said, that reference model needs to ensure that the average risk, the relative predictor weights, and the C-statistic are akin to previous models or biological rationale or so forth. Come back onto that. And we need to specify the approximate case mix distribution in the target population. So what is the distribution of predictor values? So of those candidate predictors, what's the distribution of values in the target population? The second step is then to generate a sample of n participants, so n is the sample size you're interested in, containing their predictor and outcome values. Okay, so based on all this information, we can generate for a certain sample size predictor values and outcome values. We then use this development data to develop a model. Like I said, this could be your model development method of choice. We then apply the model that we've developed back to this large target population from our setup phase. So rather than just focusing on sample size n, we can think about this some big, huge population, maybe 100,000 people, for example, that we can apply this developed model back into to test model predictions. So remember, in that large, huge population, we know the reference model's performance. For example, we know that the C statistic is whatever we've chosen it to be. We know that the calibration slope is 1 because that's perfect. We'll know the net benefit, the clinical utility. So we can see for our developed model, when we apply that back into the large target population, how worse it does. So we can estimate its performance and in particular the degradation, the loss in performance compared to that reference model. And then fifthly, we repeat steps 2 to 4 until we have 1,000 models that have been applied 1,000 times. So essentially we have every individual in the large population has 1,000 predictions, there's 1,000 models, and we've got 1,000 evaluations of those performances, and we can see the distribution of performance. So what's the distribution of the C statistics? What's the distribution of the calibration slopes? What's the distribution of clinical utility? And we can then summarize those distributions, essentially posterior distributions of model performance. And that allows us to summarize the sampling distribution. So we can say what's the expected value, what's the variability of values in the target population. Let's think about this a bit more. So in the past, in our previous calculations, for example in pmsampsize, we focused on expectations. So what's the expected shrinkage factor? We're targeting an expected shrinkage factor of 0.9. Or we're targeting an expected confidence interval width around the overall risk of 0.1 or 0.05. So we can still do that. So we can look at those posterior distributions and say, okay, for that sample size that we've looked at, what's the anticipated mean value of the C statistic or the calibration slope or the net benefit? But, and this is the beautiful thing really, is that we can now go beyond that and look at variances as well. So what's actually the variability? So, okay, the average C statistic is anticipated to be 0.7, but across all the data sets that we use to develop a model, and when we apply that back in the target population, what's the variability in the C statistic that we see? So if the expected value is the C statistic of 0.7, but the variability, it may go from like 0.55 up to 0.77 or something, that's telling us something, not just about the expected value, but about how much loss there could be in one particular data set. And that's crucial, remember, because you only have one data set to develop a model. So what happens on average is interesting, but it's not going to give you confidence that you're going to get that because you've only got one data set. So combining both of these aspects leads to this big thing that is really the heart of the piece, which is assurance. We can now, based on the posterior distribution, calculate assurance probabilities. So given the sample size and given the set of predictors you're looking at and given the model development approach, what's the probability of meeting some level of standard? So for example, what's the probability that your model that you develop will have a calibration slope between 0.9 and 1.1 in the target population? What's the probability that the net benefit of your developed model is going to be greater than the net benefit of competing strategies, such as just treating everybody and not using the model, or just not using the model and not treating anybody? And that leads to things about risk thresholds and so forth. But you get a general premise that we're talking about probability of success. And so we can be thinking about sample size now in sense of, okay, what's the probability my new model will lead to success in terms of clinical benefit? So that's really important. Degradation is key in all this. Like I said, we can look at expectation, so the expected degradation, but we can look at the variance of the degradation and also the assurance. So what's the probability that the net benefit of the model that we produce will be at least 90% of the net benefit of the reference model? So we can say, okay, we're really trying to maximize clinical benefit and impact on patients. And this sample size gives us a large probability that under the assumptions that we're making, that we're going to get at least 90% of the maximum net benefit that a true model would be able to get. Now, this needs to be repeated potentially across different sample sizes until you find the sample size that gives you the assurance that you meet. For example, it could be that you make sure that the sample size at least meets the probability of this criteria here, getting at least 90% of the reference model's net benefits. But it could be another criteria, and that's the beauty of it. You have complete flexibility in terms of what metric you're interested in. It could be multiple metrics. So it's not just about overfitting, it could be about probability of success in terms of net benefit value and so forth. So it's a much broader concept than just looking at overfitting, which pmsampsize did, and which is relevant because the more overfitting, the more degradation. But now we can look at degradation in terms of clinical utility and other aspects, which I think are probably not even more important. Now, you're probably reading this, or listening to this, and thinking, "Oh, okay, well, this is all very good, but there's some challenges in the setup phase," and let's just go through those. What sample size you start with? I alluded to it before, but you could start with a sample size as recommended by pmsampsize, or if using an existing dataset, you start with the fixed end of that dataset. And you don't start with, that's the only end that you would think about. What about the case mix distribution? I talked about the fact that you need to specify your joint predictor distribution. Well, what I would say is that, is there an existing data that you could base that on? So is there some pilot data that you got for your target population? Is there another data set, maybe a trial? Was a previous model built, and could you get access to that data? Often if you've got this existing data set, you may have that data set already. So before you do any modeling, you can look at the predictor case mix distribution and use that to inform your sample size calculation, which can then inform the number of predictors you think about and so forth. So before modeling, you can use that predictor distribution. If none of those are available, then is there a synthetic data set that you can get? So I know, for example, some electronic healthcare databases in the UK do provide synthetic data to help people who are doing pilot studies to think about their research. And that could be one way forward that you can think about. In terms of the reference model, well, like I said, this could be based on previous models in the field. Usually there are existing regression-based equations out there, and you would know C statistics of models and relative predictor weights in those equations. This idea is already embedded in PM Stability SS and will soon be incorporated in pmsampsize. And indeed, pmsampsize is going to be extended to include this work in the next, in the coming months. I'm not going to talk about it today, but you can also account for uncertainty in the reference model. So you don't have to specify just one reference model, but you can actually sample from multiple reference models. So accounting for the uncertainty, for example, in the C statistic or in the predictor weights. And that's really the long-term goal of what we want to do, is incorporate this in a Bayesian sort of idea where you sample true C statistic performance from a plausible distribution based on previous evidence. In a very pragmatic case, and I think this may often be the very default situation that we include in pmsampsize going forward when we extend it, is that you, as a user, would specify the C statistic or the R squared, which you can use to get back to the C statistic, the number of candidate predictor parameters, and assume all predictors are independent, that they're normal 0.1, i.e. they've been standardized, and that you give them the same relative weight. And actually, this concept of standardized predictors and giving them all the same weight is not far off what's actually assumed in pmsampsize as it stands at the minute. Those closed form calculations to work out the anticipated shrinkage factor tend to assume those things. And again, you've got to think about the fact that if you don't know anything, then you have to make simple assumptions and take it forward from there, and you can change those assumptions to see the impact of it. But you have to do something rather than going blindly into an error and saying, well, this sample size is probably okay. You have to make some assumptions. And so in a very practical case, assuming predictors are independent, normal 0.1, have the same relative weight, I think is a very sensible place to start. Okay, let's have a look at an example. So the aim here is to develop a model for preeclampsia outcome prediction. And the question is, okay, I'm going to develop a new cohort study to examine to develop a model, what sample size is required. In the setup phase, I'm going to say, well, I'm going to think about 10 predictor parameters based on 9 predictors. I've got synthetic data from a previous cohort study, which is telling me the case mix distribution. So of those 9 predictors, I've got synthetic data that tells me about their joint distribution. And I'm going to specify a reference model, which is a logistic regression equation with weights based on a previous model in the field, which I've extracted from the literature. And that model has a C-statistic of 0.76, a net benefit of 0.41 at a threshold of 0.5. So if there's somebody's got a risk above 0.5, then there'll be some clinical action. And that leads to a net benefit of 0.41 based on the reference model. Here's the reference model. You can see age is in there, gestational age, biomarkers like creatinine and systolic blood pressure, and so forth. But that's the model, the reference model based on the previous studies. So we're going to apply a fully simulation-based approach. I think we used about 2,000 simulations. I think 1,000 is probably fine, and sometimes 200 is fine as well. I think it depends which measures you're interested in. And we're going to look at various modelling approaches. So we're going to say, okay, let's see the impact of using frequentist lasso and ridge, or a Bayesian lasso and ridge, or the impact of using a random forest. In the paper, we look at other machine learning methods as well. And I'm going to start with a sample size of 456, which is what pmsampsize recommends here as the minimum. So in a situation where you've got this outcome prevalence, you've got a particular C-statistic, and you are wanting to meet the criteria specified in pmsampsize, minimizing overfitting and getting a precise overall risk estimate, this recommends at least 456 participants. So let's start with that and see the impact on that in terms of the broader context of all these different performance measures which you can now look at. So what are the key results? Smaller sample sizes lead to lower expected performance, higher model degradation, and lower assurance probabilities. And the required N depends on your estimands, your choices and targets of interest. Okay, so the user needs to do some work here. It's not just you plug it in and say, okay, this is what you get. You really have to think about, okay, what are you targeting? What do you want the model to achieve? You need to decide that. And so it depends on your modeling approach, the metrics of interest, the performance metrics of interest, whether you're happy to target getting those metrics that are desired on average, or whether you're wanting to have high assurance probabilities, and I think you should. It also depends on clinical context, so the thresholds, like I mentioned before, for making decisions. Let's go through some of these aspects together. Firstly, the approach, the framework, once you've been through it and it's implemented, it allows you to examine posterior distributions for any metric, and that's the beauty of it, any metric of interest. For example, let's say we're going to use a frequentist lasso logistic regression, sample size of 456. This is based on the simulation framework, this is what is the anticipated posterior distribution of the calibration slope. So we can see that the mean value is anticipated to be 1. And we have a particular variability around it. Same for net benefit. We see that the net benefit is distributed from about 90% to 100% of the total net benefit that we could get if we had the reference model. So we have the whole distribution, whereas before in pmsampsize we just had the expected value, and indeed we couldn't do a lasso. We'd had to do basic logistic regression and we would target a calibration slope of 0.9. Here we can see that the lasso, actually you're targeting a calibration slope of 1, which is actually what you want. But you can also see the variability around that. So any metric of interest. The second key result is that, like I said, lower sample sizes lead to wider distributions and lower clinical utility. So these are the results that I've just shown you for 4, 5, 6 sample size. Let's just see what happens if we, for example, said, oh, actually, I'm going to develop a model with 75 people. Now we see much wider uncertainty. The calibration slope, again, is Probably on average around 1, but there's huge variability. The calibration slope could be 0, it could be up to about 3. Net benefit, before the majority was over 90% of the maximum net benefit. Now we're looking like it's going to be less than 90% or around 90%. So the lower in the sample size has led to more variability, and here led to degradation in performance. We can present our findings as instability plots. So let's go back to the sample size of 4, 5, 6. We can, because we've got the reference model, we know the true risk, and we can plot across all those 2,000 or however many simulations you do, the variability in the developed model's estimated risk for all individuals in the target population. So we can see that at 4, 5, 6, we've got this prediction instability plot where there's a lot of variability. That even though, for example, somebody's true risk is 0.4, we see that their actual risk could be anywhere from, any one particular model could be anywhere from 1 down to 0. And the 95% interval could be, between about 0.3 to about 0.5 maybe. So there's a lot of uncertainty, maybe starting to reveal that the sample size of 4, 5, 6 may not be reliable if you're very keen to get stability at the individual level in predictions. You can plot calibration instability. So again, if you were to apply any one model back to the original data, the large target population, what's the variability in the calibration curves? You can see there's variability. But obviously this is 4, 5, 6. Let's drop the sample size again. See, it's hugely worse. So this is really exposing the problem that in the sample size of 75, there's so much uncertainty in actually developing a reliable model. Calibration performance that we'd anticipate in the target population is all over the place, and any developed model could have for any individual a prediction from 0 to 1. So really, we got no confidence in a sample size of 75 that you're going to develop a reliable model for making individual level predictions. We can summarize this in terms of metrics and statistics. So in terms of expected value, so for a sample size of 4, 5, 6, what's the expected C statistic? 0.75. What's the expected degradation compared to the reference model? Just a loss of 0.01. The expected calibration slope of 0.89. This is for a standard logistic regression. This 0.89, of course, is not too far off 0.9, and that was what the target pmsampsize was aiming for, and that pmsampsize suggested 4, 5, 6, so that's good, that's reassuring. The calibration slope, what's the probability the calibration slope is between 0.9 and 1.1, that's 0.36. What's the expected value of the net benefit of the model compared to the reference model's net benefit? The maximum you can get is 98%. What's the probability that the net benefit of the model is going to be over 90% of the maximum? It's 1. So actually, for a sample size of 4, 5, 6, in terms of the net benefit, which some people would argue is the only one that you really care about, is the population level impact. You've got a very high probability of doing well, but I showed you before, there's still instability at the individual level, so some query about that. But certainly you wouldn't want to be developing models with a sample size of 75, where your expected calibration slope is 0.45, the degradation in the C statistic is 0.08, the probability of obtaining at least 90% of the maximum net benefit is only 42%. So this is really useful, isn't it? All this information you can extract now from this sample size approach. So just to really reiterate that, pmsampsize, there's nothing wrong with pmsampsize per se, but it just focuses on the expected calibration slope for an unpenalized logistic regression. And based on the closed form approach, this recommended 456 participants to obtain an expected slope of 0.9, and here we get 0.89. But the new approach gives far more information and gives us assurance probabilities for any metric of interest and any model development approach. So it's really extending And like I said, it's embedding previous calculations but extending it to be much broader. So that was standard logistic regression, but of course now we would look at methods that we would actually be using for development, such as the lasso logistic regression, and we can see that the calibration slope now is 0.99 on average, anticipated to be, and we've got a 50% chance of it being between 0.9 and 1.1. But if we go to a sample size of 75, we've got a 13% chance. Both sample sizes have quite a high probability in terms of the expected values of the net benefit compared to the maximum. But again, only that sample size of 456 is giving you large probability that you're going to get 90% of the net benefit of the maximum model, whereas you only got a 1 in 2 chance if you had a sample size of 75. What about other methods? We could use a Bayesian lasso. Let's say we could use a logistic regression with a heuristic shrinkage, a uniform shrinkage. We can look at then their anticipated performance, and the expected values, probability of getting the calibration slope between 0.9 and 1.1. Huge, large probabilities again that you're going to get 90% or more of the net benefit. So I'm just emphasising you can look at anything. Even random forests. We could fit random forests with different tuning approaches. We could look at a depth of 3 or a depth of 15. You can see that when you've got a depth of 15, you're using a lot more complexity. So this lowers the probability of obtaining at least a net benefit of 90% or more of the maximum net benefit, down to 70%. But if you'd actually used a depth of 3, it would have been 95%. Calibration slope is probably going to be off for these methods. You got a 0 probability of obtaining a calibration slope between 0.9 and 1.1. So that just emphasizes that random forests are often badly calibrated. But again, it's telling you that the sample size that you need is potentially different for different model development approaches. I haven't even talked about the issue of noise variables. So when I was looking at my simulation study, I had predictors which I knew were important, but you could be in a situation where you go, okay, well, I know there's 10 that are important, but I also want to throw in 20 others, which I don't know they're important. They may be noise variables, but I want to see if I can improve the model. Well, the issue with that is, of course, that you throw more noise variables in there, that could well lead to more complexity, more overfitting, and therefore more degradation and more instability, more shrinkage of effects and so forth. Just to demonstrate that, let's try adding 10 more candidate predictors in, which are all noise variables into my modelling. And again, we use a sample size of 75. The expected relative value of sample information is now 0.34 compared to 0.37 with the 10 noise variables. And the probability essentially of getting a net benefit of 90% or more is now 14% compared to 68% without the 10 noise variables. So it just shows the impact of noise variables really harm model development and lead to more degradation. Of course, if some of those 10 had been important, that would have addressed some of the concerns, but you don't know that in advance. So you need to be very cautious. So this is what I mean about the approach helping you guide how many predictors you can be thinking about including. Threshold choice is also important to the calculations. So I've talked about this expected value of information or expected value of sample information, really in terms of how my model's net benefit is going to be compared to the reference model's net benefit. And I've said that really I'm aiming for that to be 90% or more. In the examples I've shown you, that's often been achieved, even at a sample size of 75. So the Frequentis lasso has a 90.4% expected net benefit compared to the reference models, and the probability of obtaining a net benefit of 80% or more is 95%. So a probability of 0.95 that the net benefit of the model you develop is going to be 80% or more of the reference model's net benefit. But the crucial thing is that this reflects a threshold choice of 0.5. And here, actually, the overall prevalence is a 0.68. So a threshold of 0.5 is quite low. Nearly everybody is going to be classed above that threshold anyway. So even, for example, even if all predictor effects are shrunk to zero, all individuals, therefore, would be above zero, because apart from sampling error, you'd have the average risk in the population would be 0.68. So this is basically akin then to saying, okay, we're just going to treat everybody. So ignoring any model, we're just going to treat everybody. And the net benefit of that is 0.36, and that's already 88% of the maximum net benefit. So really, all the model's doing is dropping down to what the treat-all strategy would be. But if you'd chosen a different threshold, for example, the threshold being 0.9, then the model's expected value of sample information would be closer to 0%, because that would reflect the treat non-strategy. So most people would just not be treated because the average prevalence is lower than that. So the threshold choice is very, very important, and that shouldn't be decided on by the sample size calculation. That should be decided on by the speaking with health professionals and patients in the field. So what N should be targeted? Recall that I've been talking about the fact that the sample size and its worth depend on the modelling choice, the metric that you're interested in, the thresholds, and so forth. So in this example, using a logistic regression with pmsampsize of sample size of 456, we would have an expected calibration slope of 0.89, but a low probability that the slope would be between 0.9 and 1.1, because we're using logistic regression without any penalisation. We'd have the expected value of the mean absolute prediction error of 0.051, the expected c-statistic 0.75, but we'd have a probability of obtaining a net benefit of at least 90% of the maximum net benefit of 1. So it really depends what you're interested in. Do you want to ensure the calibration slope is close to 1, or are you focusing more on the net benefit? So it really depends on that. Or if a user decides to use a Bayesian ridge regression, so a completely different approach in a Bayesian framework that allows for penalization, maybe an N of 75 is acceptable. If you're targeting that there's a high probability here, 95%, that the net benefit of the model is at least 80% of the net benefit that's from the reference model. But of course, if you're moving away from the net benefit and you're looking at other metrics like the calibration slope, then it could be that you haven't got enough with a sample size of 75, as I've mentioned in previous slides. Equally, a sample size of 456 is insufficient if you target a probability of 0.9, that the calibration slope is between 0.85 and 1.1, because with this Bayesian ridge regression approach with a sample size of 456, the simulation shows that only gives a probability of 0.7 of achieving that criteria. Rather, you would need to increase the sample size to about 1,000 to get a probability of 0.9 that the calibration slope is between 0.85 and 1.15. Hence, the sample size that you require is completely context specific. A statistician would just say it depends. You need to decide what's the metric of interest, what are the thresholds of interest, what would constitute an acceptable target that you would then proceed with the study based on the sample size that you got or that you are planning to recruit. If you're basing that on the calibration slope or individual level stability, you're probably going to need a higher sample size than if you were basing it on net benefit or on degradation and c-statistic. So you really need to think carefully about what are you targeting, and this is a really transparent framework to be able to do that. Right, what about computational time? Well, first of all, to note, if you want to try this out, then we've got examples data and R code available at my GitHub page. This will be embedded in a new sample size software package called pmsampsize, so keep an eye on that. So pmsampsize is obviously already there for the closed form solutions, but we're going to extend that out. The simulation-based approach can be time-consuming. It depends on the software that you're using. For example, R tends to be much faster, the processing power of your computer. It also depends on what development approach you're looking at, how many predictors you've got. So we're working on computational solutions and approximations. And like I said, keep an eye out on updates to pmsampsize. In our paper, we also propose a one sample approximation based on Fisher's information. And this can considerably reduce computational time for Bayesian approaches, but I'm not going to talk about that here. Right, let's finish with a summary. So, one framework to rule them all. I see this paper as a foundational piece. There's lots of research to still be done to make this easily applicable to the general user. But we propose that the framework gives a general framework to target posterior sampling distributions for any metric of interest which can be formed from any model development approach. So even though your reference model would, I think, be a regression, you can then use any model development approach, whether you label it AI, machine learning, or whatever, to examine the impact of using that model development approach compared to the reference model. I've shown you that the approach covers all existing sample size calculations. You can still get the expected calibration slope or the expected mean absolute prediction error, but now we can go beyond that, like I said, to look at any measure like net benefit or C-statistic, the degradation in those measures. We can look at expected values or variability, and really the heart of the paper, we can look at assurance probabilities, the probability that when you develop a model that it will lead to a calibration slope that's close to 1, that it will lead to a net benefit that's at least 90% of the maximum that we could obtain based on the reference model. We can do nice plots such as prediction and instability plots, and it's always worth saying this, but any sample size calculation is a guide. Okay, it's using the information available at the time to the user to the best of their ability to guide what sample size you need. It's not foolproof because you're having to make assumptions. If you knew the answers, so if you knew what the reference model actually was, in truth, you wouldn't need to develop a model. You're just specifying a reference model based on the information you have available in the field at the time, and then other aspects such as the C-statistics, such as the overall prevalence, again based on other information, and you use that information to give you some guide as to whether the sample size of your existing dataset or the sample size of your new dataset needs to be of a particular number of patients and events in order to do this approach with some assurance that you're going to develop a model that's worthwhile. Remember, if you're getting your study funded, those funders could give their money elsewhere. Therefore, you need to demonstrate to them there's a large probability of success. I think this is a way to do it. So I'll leave you with some references. That's the main one at the top there, the General Sample Size Framework paper that's in BMC Medical Research Methodology. And this builds on lots and lots of work from us and other people like Martin van Smeden and Pavlo and colleagues. Please check out their work as well. But anyway, I'll stop there. I hope this has been informative and exciting, and look for future work to build on this in the coming years. Thank you.